AP Chemistry, this is the last lesson of the class, the last official lesson, at least for the first semester. Of course, there will be other things popping up to help you prepare in the spring. But this is the last lesson of Unit 13, Electromotive Force. Okay, so voltage is electric potential. Voltage is comparable to the gravitational pull of a planet. You can think of voltage very simply as how hard are the electrons being pushed to move from one point to another, to move around a circuit. So it's the push of the electricity. In an electrochemical cell, voltage is a numeric measure of how strongly the cathode, copper in the earlier example, will pull electrons away from the anode, zinc in the example. So we're going to continue with our copper zinc example in the electrochemical cell. Another name for voltage used in chemistry is electromotive force, or EMF. So your book uses both, but generally in electrochemistry they like to use EMF, electromotive force, but it's the same thing as what you've learned in physics, voltage. Okay, so the activity series, we've seen that before. So the activity series shows the oxidation half of a reaction. If you look up above in the heading, it gives you a list of metals and then the oxidation reaction. Oxidation is loss, O-I-L, oil. Oxidation is loss. So you see that lithium, for example, the very first one, is losing an electron. And that electron has to go, so it doesn't just disappear into space. So it has to be paired up with another metal which is gaining an electron or is being reduced. The activity series, though, shows only individual elements, not reactions. So two things about the activity series. It does show only individual elements, not reactions, and sometimes you want to study reactions. It also doesn't have any numeric values. So the main thing we're going to talk about today is how do you put numeric values to this movement of electrons. Okay, so standard reduction potentials, and that uses the symbol E. That stands for electromotive force. The little circle means standard. So standard means it's either 1 molar concentration, 1 atmosphere of pressure, and usually, almost always, it's 25 degrees, which is room temperature. So standard reduction potentials show the voltages of different elements, ions, and common reactions. So you notice it kind of looks like the activity series, except first thing you'll notice is there's more than just elements here. There's actual reactions. There are some elements, iron, zinc, copper, the ones that we use, zinc and copper, but there's also some reactions that are very common reactions as well. In addition, you notice there's numeric values. Those are voltages, and those reflect how much the electrons are being pushed. So standard oxidation potentials, so that's E little circle with an ox for oxidation, can be obtained by reversing the direction of the reaction and changing the sign. So just take the very top one. F2, that's fluorine, is going to be reduced by giving off 2 electrons to become a 2F minus ion. It's actually 2F minus ions. If you flip that reaction around from left to right, then that negative 287 will become the positive 287 will become a negative 287. So it's just you flip the reaction around, you have an oxidation reaction instead of a reduction reaction, and then that changes the sign on the standard oxidation potential there. Okay, so the oxidation and reduction potential for each of the following reactions is defined as, for hydrogen, is defined as the oxidation, standard oxidation potential of the reduction equals the standard oxidation potential of the oxidation, which equals 0. So in other words, they defined that hydrogen either losing a hydronium atom, either gaining 2 electrons to become 2 hydrogen atoms, or hydrogen atoms losing 2 electrons to become 2 hydronium ions. They define that as 0. Sometimes scientists just do that. They say this is what we're going to call 0. Think about the centigrade temperature scale. They just defined this freezing point of water as being 0. So they just pick a place to call 0, and then everything else is in relation to that, where that 0 is. So hydrogen, both the oxidation and reduction of hydrogen into hydronium ions or back to hydrogen atoms is going to be defined as 0 potential. So there you see two hydrogen atoms, and what they're going to produce if that is oxidized is it's going to produce two hydronium ions plus two electrons. So in other words, the hydrogens lost electrons. So that's an oxidation. Here you have the reduction. You take two hydronium ions, the same ones we talked about in acid and base, you add two electrons to that, and they turn into two hydrogen atoms, which then become a hydrogen molecule. Hydrogen atoms don't exist in nature. They pair up to become hydrogen molecules. So that is the reduction. You're going from a plus and you're lowering the oxidation number. Okay, all other voltages, V or EMF, are measured against their ability to reduce to hydronium H plus ions or to oxidize to H2 plus. An oxidation or reduction reaction will happen spontaneously when the standard potential voltage is positive. So if you have a positive voltage, that means that the electrons are going to naturally, spontaneously flow. So if you take copper 2 plus ions and you add 2 electrons, that is going to produce a copper atom. So that is going to be that's going to be a reduction. And so the reduction is a positive 34 volts. You see it there in the red box. So what that means is that that's naturally going to happen. That's spontaneously going to happen. So copper will spontaneously gain electrons and be reduced. Okay, this means the copper will spontaneously gain 2 electrons and be reduced. And it gains those 2 electrons from the hydrogen in this example. This means the hydrogen will spontaneously be oxidized. So there you have the hydronium ions. They gain the 2 electrons. The hydrogen atoms. The hydrogen molecule H2 gives off the 2 electrons. They jumped over to the copper. And remember, that's an oxidation. That's a reduction potential of 0. Okay, an oxidation reduction reaction will happen spontaneously when the standard potential voltage is positive. So now we look at the other side of our copper-zinc reaction. Here you have zinc, and it's being reduced from a 2 plus down to a 0. So you take the zinc ion, you give it 2 electrons. Those 2 electrons came from the hydrogen. And that's going to give you a standard potential of reduction of negative 0.76 volts. Well, that means that it doesn't happen spontaneously. So the standard potential of reduction is negative, which means that zinc will not gain electrons and be reduced by hydrogen. If the reaction is reversed, then the standard potential becomes a standard potential of oxidation, not of reduction. And that will be positive, and zinc will oxidize to lose electrons to the hydrogen. So there it is. The zinc is going to go from a normal atom. It's going to lose the 2 electrons and become a zinc 2 plus ion, and that is a spontaneous process because the voltage, the potential is positive. An oxidation reduction reaction will happen spontaneously when the standard potential of the voltage is positive. So there we go. There's the 2 reactions we looked at on the last slide. And you see that the zinc spontaneously is oxidized to go from zinc to zinc 2 plus. That's a plus 0.76. And it gets those 2 electrons from the hydrogen. The hydrogens give off 2 electrons. They take in 2 electrons, and that produces an H2. So zinc spontaneously oxidizes and loses 2 electrons to the H+. Now you come down and you turn that reaction around. And again, for hydrogen, it's defined as 0 in both directions. So copper spontaneously reduces, that is, gains 2 electrons. It should be from the hydrogen. They come from the hydrogen. Okay, so you go from having a zinc 2 plus, a copper 2 plus, to just a copper atom, and that's spontaneous because it's a positive plus 0.34. So we've read that already. So there you go. So now what we're going to do is we're simply going to eliminate those 2 hydrogen reactions because they cancel each other out. So we put the zinc and the copper together, and we have the spontaneous oxidation of zinc. That is the anode in our electrochemical cell, plus 0.76. The copper goes in the other direction. It's a spontaneous reduction, and that's a 0.34. So the overall potential or voltage of this particular electrochemical cell that we've been working with in this unit is the adding the 2 of those together, and that gives you 1.1 volts. And that's a standard known number for zinc and copper when you put them together in an electrochemical cell. It's not just this particular problem or situation. It's anytime you put those together, they have a voltage of 1.1 volts. That's how much the electricity or the electrons are going to be pushed. So both the oxidation of zinc and the reduction of copper happens spontaneously. The standard potential of a reaction can be expressed in either of the equivalent equations. So the potential of the equation, you can do what we did here. We added the standard potential of the reduction of the cathode, that's the zinc up there, plus the so we can express that the reaction as the reduction of the cathode, that would be the copper side. You add that to the oxidation of the anode, that would be the zinc side. You just add those 2 numbers. Now what that means you had to do is from the standard potential reduction potentials table, you had to take the zinc and turn it around. It was presented as a negative number, now it's presented as a positive number because you turned the equation around. That is an oxidation reaction that you see there for zinc. So you have to turn the equation around and change the sign. And then you just add the 2 numbers together. That seems easy enough. The other way you can do it, though, well, I think that's the only way we're going to do it. Okay, so the standard potential of the reaction can be expressed in either of the following 2 equations. Oh, there I have them both. Okay, there we go. Here's the other way you can do it. No, that's it. That's the same thing. Okay, so the standard reduction potential table lists reductions only. This equation can be written as okay, so here we're going to see the alternate equation. So the standard potential of the reaction can be expressed in either of the equivalent equations. So the potential of the reaction is the reduction of the cathode, that's the copper side of the electrochemical cell, plus the oxidation of the anode. So you're going to have to get that number from the standard potential reduction potentials table and turn it around and change the sign. Or you can do the following. You can take the standard reduction of the cathode, that's the copper again, that doesn't change, but then you can just subtract the reduction from the anode. It's the same thing. You're either adding a positive or you're subtracting 2 negatives, okay, because the reduction of the anode of the zinc is going to be a negative number. So double negatives gives you the positive. Either way, it's the same equation. Okay, this form of the equation has a subtraction sign. If you use this equation, you won't need to change the sign on the number for the standard reduction potentials. Again, this might sound complicated. It's not. It's very simple. Just depends on which way you want the sign to go. Okay, so now we're going to look at our reaction here. So the anode is being oxidized. That's the zinc. So use the reverse of the reduction potential. That's the way I'm going to do that. I'm going to turn that equation around to make it a positive number, which turns the negative 0.34 into a positive 0.34. There it is right there. Okay. Okay, so the anode is being oxidized, so use the reverse of the reduction potential number from the table. So you'll see for zinc that's a negative 0.76, so you're going to turn that around. That's a reduction of zinc, so you're going to turn that around to make it the oxidation, because that's what zinc is doing. It's being oxidized. So that turns a negative 0.76 into a positive 0.76. So there you see up there the oxidation of the anode zinc is plus 0.76 for zinc. And then the cathode is being reduced, so you use the actual reduction potential from the table. You don't change that number because it's a table of reduction potentials, and copper, the cathode, is being reduced. So that's going to mean that the positive 0.34 you see in the table, you're just going to keep that as a positive 0.34. So there it is. So now down at the bottom, we have the standard potential of the entire reaction. Both sides is the reduction of the cathode. That's the 0.34 for the copper, and the and for the zinc on the left, it's the 0.76. You add those together and you get 1.10 volts. That should be a V for volts. And you see that up at the top in the diagram. There's the 1.1 volts. Now, free energy, we're going to relate this back to the thermodynamics unit. So free energy is delta G. Remember, if a reaction is going to be spontaneous, you need free energy to be a negative number. It has to be released from the reaction, just like enthalpy normally wants to be released from a reaction. So free energy delta G is a quantity that determines whether a physical process, such as a chemical reaction, will proceed spontaneously, naturally. We already learned that a redox reaction will be spontaneous when the standard potential of the cell is positive. So when you have a positive voltage, then just as we had in the last example, that 1.10, then that reaction will run spontaneously and you'll get electricity to flow. So the relation between the EMF, that's the voltage, and the standard free energy delta G is this, that standard free energy equals minus N, and that's the number of moles, which in our example that we've been working with the copper and the zinc, that's the 2 electrons. Remember, every reaction either oxidized or reduced 2 electrons. So we're going to call that now 2 moles of electrons, times something called Faraday's constant, F, times the standard potential of the reaction. So N is the number of moles of electrons, so this is the 2e minus in our zinc copper cell. F is called Faraday's constant. It's how many coulombs of electric charge you have per mole. And they just gave that the name Faraday's constant. And then the standard EMF of the reaction, and that was the 1.1 volts for the zinc copper cell that we just dealt with. In a zinc copper electrochemical cell, the following half reactions took place. Okay, so there was the oxidation for the zinc. There was the reduction for the copper. We added those two together and we got the 1.10 for the entire reaction of zinc and copper together. Substituting the values from the zinc copper cell, we get delta G minus N times F times E. So there we go. So we had the 2 electrons is represented by the 2 moles, or rather the 2 moles is represented by the 2 electrons. There's Faraday's constant, okay? So that is it, 96,485 coulombs per mole. And there's the delta E that we got from the standard reaction that we just did. And when you multiply all those together, notice there is a negative sign out in front of that equation. You get negative 212,267 joules. So since the delta G is negative, that means that reaction will proceed spontaneously. By the way, 1 joule equals 1 coulomb volt. So if you canceled your units, I didn't here, but you ended up with coulomb volts, and that's the same as a joule. So you don't need to understand any further than that. So an electrochemical cell reaction will be spontaneous when the standard potential of the reaction is positive and the delta G is negative. This means electricity will flow. In the zinc copper electrochemical cell, we computed the standard potential of the reaction as followed. Okay, so there it is. You've seen that before. Remember the standard means standard conditions. That's 1 molar concentration. 1 atmosphere of pressure if it's a gas, and generally 25 degrees centigrade or 298 Kelvin. That's not always a requirement, but it usually is. It's basically everything's at room temperature, room conditions, 1 atmosphere, 25 degrees centigrade. Okay, so the E of the reaction is plus 1.10. That does not account for values other than standard conditions. In other words, we only computed the voltage there, the 1.10, for those very specific conditions. But what if you want to do something other than those conditions? So what if we want the EMF at non-standard conditions, some other concentration, for example? So the NERST equation allows the calculation of EMF voltage at non-standard conditions. The NERST equation is, you're going to see a bunch of math here. You really don't need to understand it all. I'm just going to walk you through it. So there it is. So the voltage at any conditions, any concentrations, equals the voltage at standard conditions minus R, that's the gas constant. And you got to know which one to use there. The temperature in Kelvin, the number of moles down at the bottom, and that's the 2 electrons, and the F is the Faraday's constant. Then the natural log of the reaction quotient. So we need to be reminded of what that is. That's from our equilibrium unit. So your book expresses the equation in terms of a common log, which requires the following adjustment to the equation. There it is. So if you change from natural log ln to common log, you have to put that 2.303 conversion factor there, and that will allow you to do that. Most of you should probably be comfortable working in natural logs, but anyway, that's the way your book does it. So the standard E is the standard EMF defined earlier. R is the gas constant. Now, it's not the one you use with PV equals nRT. That one on the numerator of the units is liter atmospheres. This one is joules. So it's the other gas constant. It's the 8.31 gas constant. Temperature is 298 Kelvin. They're keeping that at 298. There's Faraday's constant. And the N is the number of moles, so that's going to be 2. Okay, now, you can simplify this equation if you realize that 2.303 is a constant number, R is a constant, T in this case is a constant, and F, Faraday's constant, is a constant. So if you put all those together, that big mess of arithmetic there, you get 0.0592. So you can simplify the equation down to what you see there on your screen. All those things become just 0.0592. All you have to deal with is the N, that 2 for the electrons. And then you got to figure out the log of the Q. That's the reaction quotient. So let's remind ourselves what that is. So the short form of the NERST equation, there you see it again up on top, same thing. Going back to the equilibrium unit, the value of the reaction quotient Q is calculated the same way as the law of mass action. So there's our total reaction there for this electrochemical cell. Copper is reduced, zinc is oxidized, and there's the equation. So if you wrote the equilibrium equation, which is what the reaction quotient is, you write it the same way as the law of mass action. Remember, you don't put in the solids. So the zinc is a solid, the copper is a solid. So you only put in the ions. Those are considered aqueous. So the zinc goes on top, the product side goes on top, and the reactant side goes on the bottom. So go back and review equilibrium if you don't remember this, although we did it a lot in acid-base. So now we're ready to run an example. Okay, so we're going to take the electrochemical cell zinc and copper, but now instead of the concentrations being 1 molar, which is standard conditions, we're going to say 5 molar of the copper ions, and 0.5 molar of the zinc ions. So these are not standard concentrations, so we use the NERST equation. There it is. So now you're going to put the 0.5 for the zinc up on the top, and the 5 for the copper down on the bottom, and you do the math on this, and you end up with a voltage, an E, of plus 1.16 volts. So notice it went up. It went up from the 1.10 that we had at standard conditions. Why? Because you have a lot of extra copper to pull in those electrons, so there's a lot of space for those electrons to move over to the cathode, and so they do it more quickly with more power, okay, or with more voltage. I shouldn't call it power, with more voltage. Okay, explanation. Since we have a high concentration of Cu, that should be 2 plus, to gain electrons, be reduced, more voltage is produced. Okay, real quick on electrolytic cells. An electrolytic cell is a kind of a backwards battery. It produces a non-spontaneous reaction that requires energy input to do work. So rather than a battery that's giving you energy, you have to put energy into it. So why would you do that? Well, an example of electrolysis from an electrolytic cell is the plating of silverware that makes silverware look silver, because silverware is not really silver. So that produces a shiny surface. So that's something that that's done by electrolysis. So that's all we need to say about that for this time. All right, so that takes care of this lesson. It's the last one you'll have. You have all weekend to get these assignments done, so hopefully you're past all your tests and you can do that. I'll be in the classroom all weekend, Saturday and Sunday. I'll give you the hours in class, and we'll see you then.